Okay, thank you for the introduction, and thank you for Santa's invitation. Also, can you hear me? Yeah. Okay.
Yes, we do.
So today I'm going to talk about on Miyaoka and Kawamata Miyaoka type inequalities. This is a driver with Liu Jie, and part of the is a driver with Masataka, Iwai, and Jiang Chen. Okay. So today I'm first let me introduce my main results. Okay. The main results. Let me first introduction some definitions. The first is we know that one of the building blocks of the minimal program is the final varieties. I mean, so what is the final means? And if a normal projective varieties, I mean, we need that k minus ks or all ks is Q cartier. Okay. So of course we don't need to the minus, but yeah, x is satisfies the following conditions. The first is that is Q factorial. The second is that his pk number is equal to 1. And then third is minus ks is ample. Okay. So this is the three conditions saying that if this is satisfied, then x is called Q final varieties. Q final. Okay. So if we only have the third conditions, that is it is called x is final. Okay, it is final. Okay, if we only have three, but replaced by another condition, is this means minus case is nav and big. Okay, then x is called weak final. Okay, just fix some definitions. Okay, so from the definition we see that Q final, of course, including in the final variety and is including in the weak final, right? So these are the categories means. Okay, so this is the definition. Okay, but in the definition we don't talk about the singularities. So I should take some remarks on the singularities. The first is that I didn't talk about the singularities. So the singularities are all coming from come from the minimal program. So it is terminal and the canonical. I think you are the experts, so I will sketch the definition of these singularities. So I just here it is coming from the minimal program, terminal, canonical, KLT, and LC. If you want, you can get the SLC and or QLC. Okay, so we will call that it is a terminal final variety or canonical final variety or canonical Q final, something like that. So if we want to emphasize the singularities, we will add the terminal or something like that on before the Q final varieties. So the second I want to take a remark is that in the singular case, we need to define the Chen class well. Okay, Chen class we need to is well defined. Should be well defined. Okay, should be well defined. If it can be first defined on the smooth locus, defined on the smooth locus, and then extended to the whole. So you call this is well defined. For example, let's just for example, smooth in codimension K. Then the CIX. I mean, this is the I Chen class is this one is well defined. For I is smaller or equal to K, right? So we can put off you can cut off codimension K plus 1 did not affect his definition, right? It is in the ith child group. So you can just define first on the smooth locus and then extend it to the whole. So we don't worry about the Chen class in our definition, right? So in particular, it is if it is smooth in codimension 2, then C1 and C2 are well defined, right? Well defined. Okay. So so in the following, I can state my theorem. The first main theorem is the Miyaoka type inequality. This is by me, Iwai, me, and Jiang this year. Just saying that if X is a terminal, of course we can we can be more singular, but let's just say stay here. Weak Fano variety of dimension n. Here, I need to say that yeah, terminal. Of course, it is a kind of smooth in codimension 2, right? So so we don't need to worry about his Chen class, the definition of his Chen class. Otherwise, we need to something like say we need to add a hat on the Chen class, hat Chen class, right? But yeah, in here we don't need to worry about it. We don't need to add a hat on it, right? So in sometimes if we only have quotient singularities, we need to add a hat on it. Yeah, but yeah, we don't need to worry about his Chen class definition. Oh, sorry, I need to write in a more. Yeah, sorry. Yeah, this is the third theorem. We just saying that the second class product is the first class n minus 2 times. It will be non-negative. It's non-negative. Okay, the first theorem. And the second theorem is that is this Kawamata Miyaoka type. Let me just simply say KM type inequality for weak funnel. Okay, this is also Iwai at the same paper. Okay, now it is let X be a terminal. Again, it is the same weak funnel variety of dimension n. Then there exists a B depending only on. Okay, the B is bigger than 0 on n such that okay, it's smaller or equal to B to this one. Okay, and this is the B is independent of X. Okay, it's independent of X. It only depends on the n. So sometimes we can say it is Bn. Okay, it is Bn. Okay, this is the third theorem, the main theorem. The third one is that in the before the first two is we are only concerning about the we concerning about the weak funnel. Now we try to ask the Bn what the Bn is. Now we can say something on the Q funnel. This is the Km type inequality for Q funnel. I mean, weak funnel is very difficult, so we just add some conditions, something like the cube funnel, right? So we can have some effective bounds. X is canonical Q funnel. Now it is Q funnel varieties of dimension n. Okay, it is smooth and smooth in codimension 2. As I said before, it is just convenient for the definition of the Chen class. Okay, then we have C1x. This the Kawamata this is the Kawamata type inequality. Okay, Km Kawamata Miyaoka type inequality. So now that the bound we can Bn we can replace by the 4. It is exactly a number 4 in this form. Okay, it is exactly a number 4. Sorry, this may not, yeah, string. It is exactly a number. Okay, so moreover, in the case n equal to 3, then we have we can have the bound more sharper. It becomes this one, 25/8. Okay, this is the third theorem. Okay. Okay, sorry, yeah. This is direct with Jie Liu. Okay, so far, are there any questions? Okay, now let's just introduce some backgrounds on this part, on the lot of inequalities. Okay, so first, let's just mention the Bogomolov-Kiyosaki inequality. Okay, it is maybe in 40 years ago. Yeah, more than 40 years ago. Just saying that if E is a torsion-free sheaf of rank greater or equal to 2, okay, let's just say R, okay, on projective, okay, let's just simply say manifold, but of course we can, as I said before, smooth in codimension 2 and something like that, okay, if E is semi-stable with respect to H is a ample divisor on X, then we have inequality, right? In an equality, just like here. It is 2r over r minus 1. Right? It is the coefficients, something like this one. And when the equality holds, it is a quotient of a brilliance, something like that. Yeah. So this is the first BG. Sometimes we just call it BG inequality. Okay. It is concerning about the torsion-free sheaf, any torsion-free sheaf. But we need a very important assumption is that the sum is stable. Sorry, I'm not going into the detail of the definition. Actually, I should mention it in the in my sketch of proof, but I might skip it. Yeah. So let's just emphasize a little bit that we need the E is semi-stable. Okay. But what about the most natural torsion-free sheaf on a variety is his tangent bundle or cotangent bundle, right? So in this case, we can concern about the inequalities on these torsion-free sheaves. So in this case, we don't need to be without semi-stable. So we don't need to worry about no, not worry. We don't need to assumption that it is semi-stable. Okay, so we just concerning about the tangent bundle or cotangent bundle. It's very natural. They are dual, so we only concern about his tangent bundle is okay. Okay, so the first is that there's some cases we need to concern. First is when KS is NF, right? Okay, in this case, the abundance conjecture predicts that this should be semi-ample, right? It should be semi-ample abundance. But of course, we don't have abundance yet, right? So in this case, we do have some inequalities, say Miyaoka Yao inequality, right? So so the first is Miyaoka Yao inequality. So what is that? This one is Miyaoka and Yao maybe in 2 years later earlier than that. I'm not quite sure the history, so if I say wrong, please forgive me. And X is smooth. In this case, it's smooth. Okay, and KS is ample. In this case, now we have an inequality like this one. Is So it is, yeah, there's an inequality like this. So the coefficients becomes much sharper. I mean, yeah. So actually, this is smaller than this one, right? In the BG's inequality, the coefficients should be here, as this one, right? So, but now we don't need the assumption that semi-stability, but we have a sharper bound, yeah, in the tangent bound case, okay, and the KS is ample in here, okay. So, so the second one is that we need to we can improve it a little bit. I mean, not little bit. I mean, in the singular case, right? We can improve into the singular case. Yeah, this is indeed we can get a. Sorry. Yeah. Sorry. Let me just take a look. Yeah. Sorry. Okay. And Peter Liu, 他急. This is 4 years ago. Okay, we can improve the singularities to KLT case. Okay, let's just say smooth in codimension 2. But they prove it actually in the hat case. I mean, say I hat case. Yeah, but to compare with our talk, we just say smooth in codimension 2 and KLT. Okay. So KS is naive and big. In this case, we do have the same inequality. We do have this inequality, okay? And the equality holds if and only if it is a quotient of a ball. But the ball in the singular case is a little bit difficult, complicated, okay? So we just concerned about the inequality. So this is the Miyaoka Yao type inequality. The first it is in the smooth case. We can generalize to the KLT case, okay? And the weak, but in the naive and big case, okay? This is the Miyaoka Yao inequality. So we have a second inequality. It is the Miyaoka inequality. Okay, we have a Miyaoka inequality. This is by Miyaoka in the 87. Okay, just saying that X is terminal and KS is net. Then C2 is pseudo-effective. That is means it cuts m minus 2. I mean this one is net or ample. I mean they are okay because we are using inequality greater or equal to 0. So if it is net, then it just take a limit of ample divisors. Okay, it is the limit of ample divisors. So that's you can say that it is for any net divisors hi. This is the pseudo-effective definition actually. Yeah, this is the Miyaoka type Miyaoka inequality. Okay, so a very natural question is that we are concerned about the KS is net. So we can ask a mirror question: is that how about the minus KS is also net? Okay. So what happened in this case? So we actually have a parallel results. But let me just, for the logical reason, I just let's from the upside down to the parallel the above one. B prime. I mean, this is a Miyaoka type inequality. Okay, so let me just say a type means just that it's very similar to this one. Okay, in this case, we do have some parallel results. The first is that by Peter Liu. 10 years ago, X is smooth, and minus Ks is semi-ample. Then C2X is pseudo-effective. In the mirror case, we do have the pseudo-effectivity of the second chain class. Okay, but yeah, I should take a remark here is that in this case, minus Ks is net does not necessarily imply that this is semi-ample, right? Right. So we do have a counter example just exactly by Bauer and Peter Liao himself. Okay. So the abundance is not is not true for the mirror part. Okay. In the mirror case, we don't have the prediction of the abundance. Okay. Okay. So this is the first Miyaoka type inequality. The second one is that in the very recent result, actually it is proved in 6 years ago, but yeah, it's so up just in this year. X is log canonical and smooth in codimension 2, just for technical reason, okay? And minus Ks is net, Then say 2 is indeed also pseudo-effective. Okay, so we generalize to the singular case, not canonical case. Okay, so this is and it does assume that minus K is semi-ample. Okay, so this is the B prime part. It's the mirror of the B part. Okay, so let's for the logical reason, then we can prove the A prime part actually by the B prime part. A prime part is the parallel to the Miyaoka type inequality. So we have a Kawamata Miyaoka type inequality. Okay. So in this case, we do have first the Peter Liu's result in the 10 years ago at the same paper. Actually, he did not prove it, but it's easy from this result. Actually, it did not show up in his paper, but yeah, this result is very natural and directly coming out from the above result. Okay, X is smooth and minus K is ample. Now it is need to ample. Then we do have a inequality. Okay, so this Bn is a constant, only depends on n. Okay, depends on n. Sorry. On n, a constant independent on x. Okay. Okay. So and the second we have a result by Jie Liu. Yeah, in 4 years ago. Okay, X again it is smooth, but now we consider that his Pk number is equal to 1. Okay, so actually it is a smooth Q-final variety. Okay, the minus Ks is ample. Then we do have a sharp bound, not sharp bound. I mean, if you have a very effective coefficients like this one. Actually, this one can be more precise. Actually, it's more precise. Depending on Q, where the Q is the final index. I mean, it can be more rationed on the Q final index, and they are some FQ, and the FQ is smaller, equal to 4 in the universal bound, upper bound. Okay. So indeed, in this the smooth case, we do have a Kawamata Miyaoka type inequality. Okay. Yeah. The proof actually is it is just by of course depends on the BAB conjecture, BAB theorem, right? If V can prove this one is not negative, then this one is directly from the BAB theorem. It is bound. So the Chen cars are all, we have a universal Bn. So the key point is prove this one. The so-called, we have proved it in the theorem 1. I mean, when we have theorem 1, then this one is a direct consequence. Okay? But this is not so trivial. I mean, it is not trivial to prove that this is actually greater than 0. Okay, this is the smooth part. I mean, you can also ask the singular part. Okay, the singular case. So singular case is the first Kawamata in 92. Okay, 92. Say X a terminal Q funnel 3-fold. So we do have a inequality, something like this. Something like this. This Bn is a constant. It's a constant. Okay, it's a constant. We do not know how what the short bound is, but yeah, later after the Q, the final index have been bound, we do have some estimate of the B3. Yeah, but at first we do not know. We just know that it is a constant, depending only on the dimension 3. Okay. So later, Iwai. This is just the theorem, main theorem 2. Okay. Okay. So we can actually say more. Epsilon not canonical. Epsilon is greater than 0. Smooth in codimension 2. And minus ks is nef and big. And this is just a weak funnel. Okay. So we do have a bound. This one is constant. Depend only on n and epsilon. But of course, we do not state it in our paper. But of course, actually, as I said before, it is concerning about the BAB conjecture, BAB theorem. So we have a BAB theorem on the epsilon not canonical by Becker, right? So once we have this inequality, then use the BAB theorem we will get. So the key point is that this theorem, okay, is the theorem. So in this case, we do have this is greater than 0, but not equal, The key is not equal, okay, because we have that this C2 is effective. So pseudo effective means that this is, of course, it is greater than equal to 0. But the key point is not, this cannot happen. Okay, this is the 4, maybe some the 4 we have, and the 5 is, of course, our main theorem 3. Okay, it's the X is Q funnel, terminal Q. Let's just for simplicity, we just say it is terminal Q funnel. Of course, it is canonical and is smooth in codimension 2, right? So we have this one. I should say that this is sharp. It's sharp. It's not smaller or equal, but it exactly is smaller than 4. Okay. Okay. So this is my the whole the background of this is the singular case. Okay, this singular case. The background of the inequalities, some related inequalities, but I may not lose some inequalities. Yeah, but this is the main line. Are there any questions? Okay. If not, let me just some sketch. Okay, a little bit sketch of the proof, and I will just very sketch. I will talk something about the terminal 3-fold case. So I will just spend several minutes to talk about the sketch of pools. The main theorem, as I said before, the main theorem is on actually it is on depends on oath. C2 is pseudo-effective, right? And the key and the key part the key technique are also similar to that one. I mean, this the theorem part is that one. I mean, it's not easy. The theorem is so for your convenience. I just say here, this one is greater than 0. I mean, this is not 0 for x is big final. Okay, KLT in codimension and smooth in codimension 2. Okay, so the key point is the key technique is similar to the oath result. I mean, yeah, need to the emptiness of the generic emptiness of the tangent bundle. Okay, generic of the tangent bundle. So, but I will not go into the very details. So the C2, as I said, it is key point is theorem 1 plus the BAB theorem. Okay, so the key point of theorem 2 is here. Theorem 3 is actually in that it depends on the rank of the maximal. I mean, yeah, destabilizing shape of TS. I mean, in the singular case, TS is not necessary. I mean, even in the smooth case, TS is not necessary to be semi-ample, right? So we have counter examples for smooth final varieties that TS is not semi-ample. So we need to consider his maximal destabilizing shift. I mean, I did not have the time to write out the precise definition because we need to say something about the slope and the Narasimhan filtration. Sorry, so we just predict that we all know his definition. So the R is the rank of the maximal destabilizing shift of Tx. So the point is divided into 2 parts. The first is greater or equal to 0, 2 to 2. This one is actually something like is easier. It's longest inequality, or our results can also get the 4 bound. The bound is to be 4. Okay. Actually they are all due back to Miyaoka. I mean, in his paper. I mean, his idea already so up there. Okay, so it is concerning about the Miyaoka, this paper, original paper. Okay, the idea is not so hard. The key point is this one, R equal to 1. I mean, this is most difficult part. In this part, we actually use the funnel foliation. I mean, developer in this 10 years. Okay, for this in some sense it also due back to Miyaoka, but it's in another paper. I mean, it is this paper. Okay, just saying that this one, if this one for F is a smooth, S to C is a smooth morphism from X to a smooth curve to a curve C. This anti-canonical can never be ample. So I mean, this one cannot be ample. So you can generalize these results to the. I mean, the C is becoming singular. C is the dimension of C is becoming higher, and X is becoming to be KLT, something like this one, and even generalize to the KLT case. I mean, KLT case. You can generalize this results to KLT case, and even to to the final foliation case. Okay, so in the final foliation case, sometimes you have such a map, something like this one, and this the general fiber of this is P1 fiber is equal to is P1. So so this one is ample. This one means that it can never be ample. So this one must not be KLT. I mean, in some sense, it cannot be ALT. You have a horizontal one cutting the P1, the curve P1, and then you will get some numerical inequalities push forward to X. I mean, it is a sorry. I just want to say something about the three-dimensional case. So I sketched the pool a little bit in here. Okay, sorry, I just sketch here. Let me just pay attention to the four-dimensional case. Sorry, are there any questions on my sketch of proof? I mean, this part we need to use the final foliation. Yeah, I'm just saying that this is also due back to Miyaoka's idea in his 93 paper, just a generalization to the final foliation case. Okay. Okay, so let me just pay attention to a three-dimension case on terminal. I mean something like it is Q final or not 3/4. Okay, so as I said, we don't need to consider about the canonical and smooth in codimension 2. We just simply say it is on the terminal case. Okay, so in this case, our aim is to do a classification. Okay, so to do a classification, we have two directions. The first direction is very rough. I mean, its minor case is net. In this case, we try to do a classification on this case. So in this case, we do as a corollary of the previous result, we do have some classification. For example, if this one is equal to 0, if one of the following is holds. I mean, first S is admits. Admits are a coset eta cover by a P1 bundle over an abelian surface. I mean, it's just something like this one, and you have as a cover, X prime. This is a eta. Actually, it is eta in codimension 2. I mean, it is eta in codimension 2. Just verified over the singular points. Then X prime is a P1 bundle, and it is a P1 bundle. Sorry. Yeah, there's a P1 bundle over an abelian surface. There's something like this one. Okay, and the second is that X itself is already smooth, and admitting a locally trivial vibration. Okay, over an elliptic curve. Where the fiber are rationally connected. I mean, in this case, we don't have a coset eta cover. I mean, itself it has already a vibration over a elliptic curve. I mean, the fiber is something a rational connected curve surface. Okay, it's locally trivial. I mean, the fibers are the same in the algebraic sense. Okay, the third one is X is rational is already itself is rational connected, and his ks cannot be big. I mean, his minus ks, actually this one cannot be big, right? And then the set Rx. This one is the raised basket. So I guess the audience are very familiar with this one. I mean, so yeah, just let me just mention that this is the raised basket, but it is only the local index. I mean, we forget another message. I mean, sometimes the raised basket is RB, right? It is R here. It is concerning about these singularities, but we just concerning about the local index. It is Rx. Okay, there are only 8 times. And we can write out the 8 times, but yeah, let me just omit it here. Yeah, it is not so interesting in the 18. But of course, we can if we can sort out every case can be actually happen, that will be great. We can only solve that only the 260. Yeah, I'm a little bit forget that. Yeah, it is this one can only happen if I remember correct. Or A. Yeah, sorry. Yeah, but only one case can actually happen. Yeah, the other ones we don't know. I mean, just the first one case, we do have an example on this one. Okay, this is just an implication of the first case. I mean, it's an application of theorem 1. Okay, let me just say something about the second case. I mean, in the 3-dimensional case, I mean, it's the Q funnel. Another direction. I mean, this direction is very roof. Its minor case is left. Okay. Now here we are very restrictive. I mean, this one minus case is ample, and his Picard number has to be 1, and his Q factorial, right? But of course, it is also one of the building blocks in the minimal program. In some sense, you just take a Q factorization and run the MMP. Finally, you will get a Q funnel varieties, Q funnel divisors, right? So we do interested in how to classify these ones. But we also, of course, we know that the first one is the smooth case. We do have a classification. I mean, it is maybe or this one. I'm a little bit forgot about the precise numbers. Okay, yeah, it is in my memory. It is actually recently we find a gap here, but not me. I mean, people will find a gap here, but I'm not quite sure it is or not. Is this number or this number? Sorry, yeah, but of course this is by several peoples and Jita, Mori, Mukai. These are well known, right? So in the smooth case, we do have a very clear classifications. But in the singular case, we know that the things is different, right? So things are very different. So we only have a partial results, some partial results. Sorry. Yeah? Say, for example, in the Grossstein case, Mukai and say Sano and Campana lecture. I mean, maybe I will. I may, due to my knowledge, I may lost some people. So if I lost someone, please forget me. I mean, we in the singular case, we only have some partial results, and the most partial results is coming from the index. We concerned about the index. Okay, the index is introduced by. Not introduced. I mean, it is started by, for example, Stucky, Prokhoff, and so on. In the index, I mean, we use this one. The first one is the max. We have several kinds of index actually, but we use this one. Okay, so we do use the QX definition. I think I already write it once. So let me just, A belongs to his real divisor group, and we have a QW. Okay, this is actually the same, but it's actually this one we replace by Q by just linear equivalent. Okay, the B is belong to this one. Yeah, it's exactly the same, almost the same. I mean, of course, from this we know that QW, sorry, is divided. QQ is divided by QW. Okay, so and we do know this one is belong to one and belong to these numbers. Okay, so in the higher index, we have some classifications. It's actually very clear. I mean, by say Popov with sounds. And the third I should remark is the grade ring database. I mean, this database, yeah, of course, Alexander is here. Yeah, I mean, yeah, they help me a lot. This database help us a lot to do a classification in the three-dimensional case. Okay, okay. In this database, we can see that the Hilbert series. Yeah, I'm not quite sure. It maybe 15,000. Yeah, possibilities of Hilbert series. Okay, so this we know some results on the Q-final favors just to do the classification. Okay, the second remark is that there's two key tools in the classification of three-dimensional. The first one is Weiss-Oberford Riemann-Roch formula. The second one is Kawamata's inequality in dimension 3. So with our results, we have in this case terminal Q-final three-fold case. Then this one actually is, as I said before, is smaller than this one. So with this precise result, we can actually rule out a lot of cases. Sorry. Lots of the possibilities. Of the Hilbert series. I mean, maybe we can drop 20%. I did not run the precise the program yet. I mean, I'm not quite so sure we can cut out how many, but yeah, as our experience, we can cut out a lot of the possibilities in this database. I mean, yeah. Actually, I do. If our results is indeed true, we do want to, yeah. Sometimes we search this one, and it's not so convenient. I mean, for example, we have something like the bx. That bx is equal to say 2, say 1, yeah, minus. Sorry, it's not this one. It's the say 1 square, say 2, say 1. I mean, this is bx. If we can, input something like this one, and we can run out how many those possibilities contained in the range, it will be very, very convenient for us. I mean, yeah. But now we have to download those data in GRDB, and then put it in an Excel, and then to check as if those numbers are in our range. Yeah, in some ties. Yes. But of course they help us very, very much. Yeah, this database. Okay, the first one is the first remark. And the second remark is me and Liu Jie and I. Okay. Possibly Prokofiev. I'm not quite sure if he will join or not. I mean, we just communicate with him, and yeah, but I'm not quite so sure he will join or not. He improve. I mean, improve the actually the above bound to this one. Actually, in this case, this I mean the equality holds if and only if it is this case equal to 3, 7, 7. I mean, and the Q equal to QW equal to 5. I mean, this the equality only holds in only one case. I mean, in this case, and we can rule out this case, and then the bound drops to here, and then this case the equality holds if only if another case is here, and Q equal to QW equal to 4. And then we can also, some different methods to rule out this case, and then rule out this case, and we get a short bound here. Okay, this is the classifications of the in the 3-dimensional case. I think I will stop here because I left several minutes to have some communications. So thank you for your listening.